Bismillah ar-Rahman ar-Rahim. Let's start with chapter 1, Physics and Measurements. We are going to talk about the three fundamental units. Why fundamental? Well, because they are independent of each other. You cannot derive time from mass or mass from length. They are independent. And also, you can derive all the mechanics units using those three units. For example, what's the unit of force? The unit of force is Newton. Type, what is Newton? Well, we know that F is equal MA, kilogram meter per second square. So Newton is nothing but kilogram meter over second square, and etc. etc. All the units can be derived from those fundamental units. Let's talk about length. Well, we know that velocity is equal distance divided by time, or delta D over delta T. So how we can figure how we can measure 1 meter? Well, D is equal V multiplied by T. What's the speed of light? Well, the speed of light is this value approximately, let's say 310 to the power 8 meter per second, and then we multiply it by 1 over the speed of light in terms of time, 10 to the power 8. So we end up with the value 1, and the unit is meter. Of course, this is an approximation. The actual value is this number. So this is how we determine accurately a 1 meter. This is the standard. For the mass, we keep a piece of alloy. This one, a piece of alloy. We keep it in a place where the safe place with no humidity and no variance of temperature. And basically it has a mass, and we call this mass is 1 kilogram. So that's the standard, and they can make a copy from that mass and distribute it around the world. So this is the 1 kilo. For the time, we use the vibration of cesium-133 atom, and the second is this number, this huge number, times the period of the vibration of the cesium. So the period of vibration of cesium-133 is very accurate. So if we multiply it with this number, we'll get 1 second. If we multiply it with this number, we get 1 second. It has an advantage that the vibration of the cesium atom does not depend on gravity, does not depend on temperature, does not depend on it's accurate. It's accurate. Powers of 10, well, we have the kilogram, we have the mega, we have the giga, we have the tera, we have the peta. Like now, for example, in the hard disk storage, it's commonly to see that we have 2 terabyte and 4 terabyte hard disks. When you go smaller, DC and centi and milli, micro, nano, pico, femto, etc. we come to identify density, and density is mass over volume. So you can basically, he has an example, a lead and styrofoam, and basically you can have two objects with the same volume, but they can differ in density because density is mass over volume. Quick quiz. In machine shop, two cams are produced, one of aluminum and one of iron. Both cams have the same mass. Which cam is larger? طبعا the aluminum cam is larger. Why larger? Because it has less density. Modeling an alternative representation. Well, we are going to use that a lot when we solve physics problems. You need to simplify your problem before you can solve it. One way to simplify it is use a geometrical model. Here you wish to find the height of a tree but cannot measure it directly. You stand 50 meters from the tree and determine that a line of sight from the ground to the top of the tree makes an angle of 25 degrees with the ground. How tall is the tree? Well, we will come to this, we will repeat this again when we talk about vectors, but it's not wrong to mention it more than one time. A is a vector. This is the x-axis and this is the y-axis. The length x is equal the length A, يعني A without a vector sign, that means the length of A. So the length of A cosine theta, and y is the length of A sine theta. Tan theta is sine over cosine. So that means sine theta is equal y over A, cosine theta x over A. And that means tan theta is equal y over x. So here we put the 3. So this is y, and this is x. So tan theta is y over x. We know theta, so bring tan, and then we can determine y. Also, we have read it from the book, simplification method, analysis method, structural method. Depends on your problem. So let's come now to dimensions. So here we start with mass, and we give it the letter M. Time, we give it the letter capital T. Length, we give it the letter L. Why M? Well, because sometimes you use gram, sometimes you use kilogram, sometimes you use pound. So it's mass. So we give it the letter M. For the length, sometimes we use centimeter, inch, feet. So we give it the letter L. And time, to be consistent with them, it's capital M, capital T, capital L. For example, A, the acceleration, is meter per second square. The units, the dimensions of A is L, length, over time square, over time square. Here, when we write A is equal B, that means A and B have the same power. the same units and the same value. That's the meaning of equality. That's the meaning of equality. So if the dimension, if d is equal 30 meter, then the dimension of d is L. When v is equal 20 meter per second, the dimension of v is L over t. Here, x is equal half at squared. So in the left-hand side of the equation, or the equality, the dimension is L. Half is a number, so it has no dimension. A is meter per second square, so L over t square, multiply by t square, so t square will go t square, so right hand side of the equation equal the left hand side of the equation. So we can write that x equal, but without the number, a to the power n and t to the power m. So a to the power n must be equal to 1. And t to the power m must be equal to 0. M must be equal to 0 because, again, we have equality. So when we have the equal sign, it means three things. Value is the same, units is the same, and power is the same. Right. Quick quiz. True or false, dimensional analysis can give you the numerical value of a constant of proportionality that may appear in algebraic expression, and the answer is wrong or false. Why? Because this equation, the dimension of it is L, and this equation, the dimension of it is L. So the dimension cannot give me the numerical value of the constant. Cannot give me. It will just tell me that the equation dimensionally is correct, but does not necessarily mean that the equation is correct. Does not tell me that if the equation is correct or wrong. It will tell me the dimension is correct, but not the numerical values. Analysis of an equation. Let's analyze this equation. V is equal AT. V on the left hand side is length over time. Let's see the right hand side of the equation. It's AT. A, the acceleration, is length over time square. Multiply by time. So it will end up with length over time, which is the V velocity dimension. Now let's try to solve this a little bit confusing equation. Let's redo it again together. Maybe it will make it a little clearer. So we have A, K, R to the power N, V to the power M. You need the value of N and the value of V. K is just a number. So it has no units. It has no dimension. It has no, not units, no dimension. So let's see the left-hand side. So it is length over time square. Now let's see the right-hand side. K, no dimension. R is length to the power n, and V meter per second square, so length over time square. Sorry, length over time to the power m, to the power m. Now let's try to simplify the right hand side. Well, here L to the power n and L to the power m, it will be L to the power n plus m. And at the bottom, we have t to the power m. In the left hand side, we have L t square. So right away, we can know that m is equal to. Why? Because t square is equal t to the power m. That means m must equal to 2. And that's the first one. The second one, L must equal Ln plus m. So the second one is L must equal Ln plus m. So that means n plus m must equal to 1, because here the power of L is 1. Well, we have two equations. M is equal to and n plus m is equal 1. That means n plus 2 must equal 1. N is equal minus 1. So m is 2 and n is minus 1. So then A is equal K R to the power minus 1 and V to the power 2. However, R to the minus 1, so it will come down. So it is KV square over R. Conversion of units. Conversion of units. I saw from my experience a lot of confusion in conversion of units. Some students will find it very confusing, not hard, but confusing to convert from one unit to another. And I will ask you to convert 1,000 riyal to how much dollars? Can you figure it out? Well, let's try. So let's see. We write first 1 Qatari Riyal is equal to how much US? 1 Qatari Riyal, how much US? It is 0.274. Okay. Next, I have 1,000 Qatari Riyal. So how much is it? It is X. And then after that, I do a cross product. It means X multiplied by 1 is equal to 1,000 multiplied by 274, which is equal 274 US. Now let's do the reverse. I have 1,000 US. I want to know how much Qatari Riyal. Well, I know that 1 US is 3.65 Qatari Riyal. So I do the cross product, X multiplied by 1 is equal 3.65 multiplied by 1,000, and that means X is equal 3,650 Qatari Riyal. When it is with money, it's very clear, very easy. When you go to physics, it's so confusing. Anyway, if you ever got confused in converting units, just write this example, US to Qatari or Qatari to US. You write this line, the ratio between the two values, and then the quantities that you have, and then you go on. So this is the ratio, like this. This is the ratio. This is the ratio.